It seems that we had a small accident last night. Professor Sprott was working on his computer while it was generating a table of random numbers, and he accidentally got connected to it. This doesn't seem to have done him any lasting harm, but it's affected his sense of direction. So I hope you'll bear with us. And now I'd like you to give it up for that wonder of physics, for that king of chaos, Professor Clint Sprott!
Welcome to the wonders of physics. Oh, welcome to the wonders of physics. Now, really, there's nothing at all wrong with my sense of direction. In fact, what I wanted to demonstrate to you was something that in physics we call a random walk. Now, all of you can go on a random walk if you want to. Go out to a big field somewhere with a coin, like a quarter, and flip the coin. If it comes up heads, turn to your right and take a big step. And then flip again. If it comes up tails, turn to your left and take a big step. And keep doing that over and over and over again, and you will execute what we call a random walk. Now, we're going to be talking about examples of randomness today, and we're going to be using the computer to demonstrate some of these things. And the first demonstration here is what you would see if you were in an airplane flying up high above someone who was doing a random walk. You would see them go in a pattern something like this. Now, if you can't see it down here, watch the monitors on the side of the lecture hall. Because you see, a very complicated pattern is being formed. And in fact, that pattern has a name. And it's a name we're going to refer to later in the lecture, so I'm going to say it now, and then later on I'm going to ask you if you remember the name. And the name is a fractal. A fractal is a complicated object that is more complicated than a line, but less complicated than a surface. It's an object with a non-integer dimension. And we'll come back a little later and talk more about fractals. But before continuing to talk about randomness and a related idea that we call chaos, I want to talk to you a moment about the opposite. And that is what we call regular or periodic motion. And for this, I will need a volunteer to help me demonstrate. How about you? Come on down here. Come down here, turn around and face the audience, and tell us your name.
My name is Annika Selvag.
Annika. Annika, have you ever gone bowling?
Yes.
Would you like to go bowling today?
Sure.
Good, because if you'll turn to your right, go over to my assistant, Mr. Lovell, and we will take a bowling ball that weighs 16 pounds and suspend it from a wire from the ceiling and make what we call a pendulum. Now, a pendulum is any object on the end of a string or a wire that is free to swing back and forth. Now, Annika, would you try to hold that right by your nose? Good and tight, and we'll help you a little bit so it doesn't pull you over. Now, when I say I want you to let go, you ready? Let go. Put your hands down by your side, and don't move. Give Annika a hand. Now, this, in fact, is an illustration of what in physics we call periodic motion. That is to say, the motion of the pendulum is very regular. We can predict with great accuracy exactly where it will go. So much so that we can put a person's very safety at stake. We're that certain that we know how to predict such things. Now, there are many things in physics that are extremely predictable. Here's another example of a pendulum. It's an upside-down pendulum, and it has a name. Does someone know what this is called? What is it called? That's right, it's called a metronome. And a metronome is so very regular, we can use it to keep the beat to the music. So, there are many things in nature that are very regular like that, but those are not the things we're going to talk about today. Today we're going to talk about things that behave in a very irregular manner. Now, there are many examples of things that aren't quite so regular, and I want to show you one now. Here's something much like the bowling ball pendulum, except what kind of ball is this? That's right. It's our tennis ball pendulum. So I'll start it swinging. And you notice it's not quite such a simple motion as was the bowling ball. It's going around in a funny way. And the reason it's behaving in such a funny way is not because it's a tennis ball. There's no fundamental difference between a tennis ball and a bowling ball. But rather because inside the tennis ball is a magnet. And underneath the tennis ball are 4 other magnets. These blue things are magnets. And you can tell that the tennis ball is attracted to these magnets. But the important thing is this pendulum, which differs only slightly from the bowling ball, exhibits a very different kind of motion. It exhibits what we call chaotic motion. Now, chaos looks a lot like random motion. It looks like it would be difficult to predict. And indeed, it is difficult to predict over the long term. But over the short term, it is in fact quite plausible to predict the motion of such a pendulum. But it is extremely sensitive to the starting condition. That is to say, if I start the pendulum here and let it go, it will do a very different thing than if I start it from here and let it go. For a little while, it will look the same, but then after a while, it will be doing something completely different. So this sensitivity to starting conditions is a characteristic feature of chaos. Now, I want to emphasize the motion is completely deterministic. This sensitivity to initial conditions comes up in many different areas. And one area it comes up is the weather. You know, one of the first applications of these ideas was for explaining the weather. And it goes by a funny name. It's called the butterfly effect. The butterfly effect says that a butterfly flapping its wings in Brazil, for example, can set off tornadoes in Texas. And it's perfectly possible because the weather is a chaotic system that is very sensitive to the starting conditions. So the present weather determines the weather tomorrow and the day after and the day after. But very tiny changes in today's weather can make an enormous difference in the weather, say, a week from now. And so this sensitivity to initial conditions is a characteristic of chaos. Now, chaos comes up in many different fields. I've talked about it in connection with the weather. It also comes up, for example, in astronomy. You know, there's a planet called Saturn. Do you know about Saturn? Saturn has a moon, a satellite that revolves around it called Hyperion. Hyperion, unlike our own moon, however, is not round. It's not a sphere, but rather it's a potato-shaped object. And when Hyperion orbits Saturn, it tumbles, and it does so in a chaotic fashion. It would look random, unpredictable to you, but in fact it's obeying simple laws that just happen to give complicated behavior. Another example is in medicine. You know, ordinarily your heart beats in a regular way, like the metronome. But there is a condition called fibrillation when your heart begins beating in a very erratic manner, a chaotic manner. And so these ideas are applicable to medicine. People are even trying to apply these ideas to economy, trying to understand the business cycle and even to predict the stock market using some of these ideas. And if anyone succeeds, maybe they'll get rich. Well, you know, there's a classic problem that involves chaos, and that is something called the three-body problem. Now, you know, the Earth has a single sun, right? You see it every day. And the Earth orbits around that sun in a very periodic, predictable manner. How long does it take the Earth to go around the sun? 1 year, exactly so. You know, there are a lot of adults that don't know the answer to that question. There was a recent survey that proved that. But that's right. The Earth goes around the sun once per year. But you know, there are many stars that come in pairs. And there are probably planets that orbit those pairs of stars. And this is what happens if a planet orbits a pair of stars. It's the three-body problem, a planet plus 2 stars. And you see the orbit is very much more complicated, even though the physical laws are exactly the same as the law that makes the Earth orbit the sun once per year. So the introduction of that third body makes all the difference in the world. Now, we can illustrate this sensitivity to initial conditions by starting the demonstration over. Now, this time, we start with 2 planets that start with ever so slightly different speeds. And you can see for a long time they go together. It looks like just a single planet orbiting. But if you watch it for a while, you will notice that after a while they begin to separate. And they get farther and farther apart until eventually what one planet is doing bears no relation to what the other planet is doing. So this is the sensitivity to initial conditions. Now watch here, for example. You'll see they get farther and farther apart. And in a moment, one will be orbiting around one star and the other will be orbiting around the other star. Now, while we're speaking of pendulums, here's another kind of weird pendulum that goes up and down like this. It has one kind of motion like that, quite periodic and quite regular. And then there's another kind of motion that's like that, again quite periodic and quite regular. But the two motions are clearly coupled together in some way, and in fact if I start it kind of up like this and let it go, you will see it exhibits complicated motion. In fact, the motion is chaotic. There's nothing about it that's regular. It doesn't repeat. But yet if you watch it for a while, eventually you will see it settle into a periodic kind of motion. Remember when I came in the room, I was showing you a random walk, the kind of thing that occurs if we flip a coin, make our decisions based on pure chance. Now, there are many examples of randomness in nature. In fact, you're all breathing randomness right now. What are you breathing? That's right, you're breathing air, and air is made up of gases, and the gases consist of tiny molecules, much too small for you to see, and these molecules are in rapid motion. It looks like a swarm of bees if you could see them with a very powerful microscope. And so this is an example of random motion. The molecules are moving in a way that's so complicated that there is no hope for our understanding the motion of any given molecule. Now we have a demonstration here that will illustrate random motion, and you'll have to watch it on the television monitors. You see over here some BBs that are mounted inside of a holder which will vibrate and cause them to shake. And when that happens, you see something like what you would see if you could see the molecules moving in the air that you're breathing. And if you were to watch how a particular BB in this demonstration, or how a particular molecule in the air moves, it would move in a very complicated fashion, essentially random. So that's randomness, and randomness and chaos have a lot in common, except chaos can occur even for systems that we understand and can calculate and that are deterministic. Now, while we're talking about pendulums, here's another pendulum. Swings back and forth, much like the bowling ball. But you notice if you watch it for a while, something is happening. Can you see something happening? What's happening? What's happening? Yeah. That's right, it slows down, and eventually it will come to rest. And do you know why that is? There's a name for what makes it do that. Someone else. Friction, that's the word. And all moving systems have a certain amount of friction associated with them. And the friction always causes the motion to eventually stop. And so that's what you see. But you know there's a way to overcome friction. And I want to show you that right now. If we move the whole table back and forth, we are putting energy into the pendulum at the same rate that friction is taking it out. Now, friction takes the energy out and converts it into heat. But in this case, the pendulum will swing forever, as long as the table is moving. You also notice it's a periodic motion. But watch, if I turn up the motion a little bit, like so, you will notice a very different kind of motion. It's the same pendulum, and yet in no way is it now reproducing. It's not regular, like the metronome and like so many other systems, but it's doing a much more complicated sort of thing. And so this is a feature of chaos, that you can sort of turn it on and turn it off with small changes of something. And in this case, the speed with which the table goes back and forth is, in fact, the thing we're changing. Now, we have this demonstrated on the computer over here as well. You'll see a pendulum swinging back and forth, and it's exactly solving the equations on the computer that governs the motion of this pendulum. And you can see it's a regular swinging back and forth, very periodic and repeatable. If we make it swing a tiny bit harder, on the other hand, just as we sped up the table here, you will see on the monitors on the side that, in fact, it goes through complicated motion, like over here. So this is to prove to you that we really understand what's going on here. The equations that describe the system are simple equations. You can write them down easily, and you can have the computer solve them. And you get exactly the motion that's observed. So there's nothing random about this. It's completely deterministic. Have many of you seen a gadget like this? Have you seen these? Where you will see these is in airport gift shops. If you ever go traveling, every airport gift shop always has one of these sitting out there going around, and it's really just a toy. You buy one and you put it on your desk or somewhere at home and just watch it go back and forth. But you notice it, in fact, is exhibiting chaos. In fact, it's exhibiting both periodicity and chaos all at once. Because you notice the outer ring is moving back and forth in a perfectly periodic way, whereas the inner ring is in a very complicated motion. And so we have both things going on all at once. It also looks like perpetual motion, doesn't it? But it's not. There's no such thing. Okay, so that's our chaotic toy. Now, let me show you another thing here. What's this? Ping pong ball. Right now, I'm going to put the ping pong ball in a little glass dish here. And can you see what's underneath the dish? What is that? That's right. Someone said it's a speaker, just like on your stereo set at home. And I'm going to turn it on. And you know, a speaker works by vibrating up and down in this case. And if I turn it on and make the speaker go up and down rather slowly, you see, eventually the ball will start to bounce. And if we wait a minute, you will notice the ball is bouncing in a very regular manner, quite periodic, just like the metronome, right? But if I turn up the volume on the speaker a tiny bit, like so, something quite different happens. Nothing regular about it at all. It looks totally random. Sometimes it goes high, sometimes it goes low. And so this is simply another example of one of these deterministic systems, a system that is predictable by simple equations, that can have regular periodic behavior, and it can also have totally irregular chaotic behavior. Now, back to our little oscillating cart, I want to show you why some things are periodic and other things are chaotic. And I want to show you a particular kind of thing here that we call a potential well. And I have a ball here which will roll back and forth in this trough, like so. And the thing I want you to notice, first of all, there is friction. Friction causes it to slow down. The motion gets smaller and smaller. And yet, if you notice the time it takes the ball to go out and come back, now what? Well, it's Albert Einstein. Dr. Einstein, please come in. It's a pleasure to have you here. It's quite a delight. In fact, we were just speaking of randomness and chaos, and I know these are things you've thought about.
Oh, this is a very, very important subject. What are you telling them?
You have often been quoted as saying that God doesn't play dice. Did you say that?
Shall I explain a little bit about what I meant?
Please tell us what you meant.
Okay. First, have you talked at all to these wonderful people about determinism?
Yes, we have. Determinism determines the way all these things operate.
Oh, very wonderful. You all are experts on determinism now, no? Yeah, very good, very good. Professor Sprott is a wonderful instructor, I know this. Now, what I meant when I had that very often quoted quote, that's a good thing to have, was God does not play dice with the universe means that all actions in the universe are governed by physical laws. I did not mean that everything could be understood. In fact, chaos is a very, very good example of things that cannot be understood completely, but they are still governed by laws. You know, there are some things that people say are random. In fact, the case in point, the thing I was talking about was the quantum mechanics. You know the quantum mechanics? Yes? No? Maybe? Yes. Oh, you should not worry about it. I don't like the quantum mechanics. In fact, that's why I was saying this quote. Well, I think I have taken up enough of your time. Are you going to be giving these people an exam? Do you want an exam? No. No. Will you give them an exam?
No, no exam today.
Oh, this is a very wonderful thing. This is the kind of course that I like to take. Because my professors, they said I would not amount to anything because I could not count and I could not pass exams. Well, enjoy yourselves, have a good time, and thank you for Professor Sprott.
Well, that's quite a surprise treat to have a visit by Albert Einstein, especially since he's been dead for 30 years. Now, we were talking about when things are periodic and when they are chaotic. And when we have a well that has the property that the period of the motion, the time it takes the ball to go out and come back, whenever that is independent of the amplitude of the motion, as it is in this case, we can only have periodic motion, as we do here. That is what we call a linear oscillator. Now I want to show you a nonlinear oscillator. And nonlinearity, well, we should stop and describe this object. Have any of you been to Yellowstone Park? You know, in Yellowstone Park, they have natural geysers. They do very much like this. And in a natural geyser, what happens is there are crevices that run deep down into the earth, and water, rainwater, goes down into the crevices and is heated from below by the very hot rocks that are deep inside the earth. And that water eventually will boil. Do you know the temperature water boils at? Does anyone know? Someone said 212 degrees Fahrenheit or 100 degrees Celsius, except that's wrong. That's right only at atmospheric pressure. The water at the bottom of a swimming pool or at the bottom of the ocean or at the bottom of a long column like in a geyser, in fact, you can heat quite a bit hotter than that because it's under pressure, like in your pressure cooker at home. And so it doesn't boil until it gets very, very hot. It's superheated. But eventually, of course, it boils. When it boils, the pressure is released, and then it all boils very vigorously, and we get an eruption, and the water goes flying up. It cools down, and it catches. It runs back down into the crevices. The heating begins again. But I show it to you now because it's an interesting example of periodic behavior. You know, there's a famous geyser in Yellowstone. Do you know the name of it? What? Old Faithful. You ever wonder why they call it that? That's right. They call it that because it goes off with considerable regularity, about once an hour or so. Not perfectly regular, but quite regular. So we were talking about a nonlinear oscillator that has the property that as the amplitude of the oscillation gets smaller, the period gets longer. Can you hear that? Unlike the metronome, which always ticks the same, here it ticks fast and then slower and slower and slower. So that's a property of a nonlinear oscillator, that it does that. Now with nonlinear oscillators, we can have chaos. And in fact, we do that by simply making the table shake back and forth. Now if we don't shake too hard, like we're doing now, we get periodic motion. After it settles down, it takes a moment for it to settle into a kind of a periodic motion, much like the pendulum swinging back and forth. But a small change in the system, like making it swing a little bit higher, like so, and it goes into a much more complicated kind of motion that doesn't repeat. It, in fact, is chaotic motion. And so that is a feature of chaos, that it always involves a nonlinearity of some sort, and this is one. By the way, this is a particular mathematical shape. This shape is y equals x to the fourth power. And so we sometimes call this a quartic well. Quartic means 4. Now, if that interested you, here we have a funny gadget that is more complicated than either of the other ones because it has 2 wells here, and then it has a hill in the middle. And I will start them together over here, and those of you will have a little trouble seeing it, but that will take care of itself in a moment. Because I'm going to shake it back and forth, sort of gently, and you notice that if I don't shake too hard, the balls kind of move back and forth together, and it didn't much matter where they start. They would lock into this condition where they're doing the same sort of thing. They're not strongly dependent on the starting conditions. So this is not chaos, but if I turn it up a little bit more, like so, you will see, indeed, we get chaotic motion, and the 2 balls are doing 2 quite different things, even though they started exactly the same, and they're being shaken back and forth the same. While we have this oscillating table, let me do one last thing with it, and that involves a bucket, which has something in it. What is it? That's right, it's just ordinary water. Now, one thing we often do with a bucket of water is to simply swing it over our heads like this, and it doesn't spill, right? But today we're not going to do that. But rather, I'm going to put a little bit in our aquarium. Now, I bet most of you have fish in your aquarium, right? Okay, we don't have any fish, but then for what we're going to do, we really don't need it. Because I want to show you something, and let's put this up so you can see it a little bit better. And get this out of the way. And turn on a light here so you can see it. And if I start the table moving back and forth, what do you think will happen? That's right. Someone said it will make waves. Well, let's see. If we move it back and forth like that, indeed it makes waves. And I think on the television monitors, you can see the waves going up and down. If I turn it up a little bit higher, what will happen? The waves will get bigger, but more importantly, they change their character. It no longer is a simple kind of a motion, but if you were sitting there, you would be sliced around in a very complicated kind of way. And so waves can be simple, periodic things, but they can also be complicated, chaotic things. Now, let's put a little bit more water in there because I want to do one other thing with the water for you. And I want to have plenty of water in there. I have here a little bit of red dye. Now, if I put a little bit of this dye in the water, what do you think will happen? What? People say it will turn red, and that's a good bet, but Old Faithful, the water won't hurt you. People say the water will turn red, but do you think all the water will turn red or just a little bit of it? All of it? Just a little bit? This is good. In science, we like to have different opinions as to what will happen. These are called theories. And it's good to think of as many different possibilities as you can, but then we don't just argue among ourselves about which is right, but you have to go into the laboratory and do an experiment, and then however the experiment comes out, then everyone has to agree that that's what happens. So we're going to do that, and I have a little thing like an eyedropper here. I'm going to put a little red dye in here, and you'll have to watch on the TV monitor. And you see, it really doesn't turn the whole thing red. All that happens is the dye just kind of sits there in the water. Now, what will happen if I start shaking it back and forth? Everyone says it will mix. Well, let's shake it back and forth and see. And there are waves there. You can see the waves. Is it mixing? It's really not. And that's because a simple wave like we're making now is a periodic thing. And you don't get mixing from periodic behavior. To get mixing, you have to have chaotic behavior. And let me turn it up a little more to get the chaotic behavior. A little bit more. And at that point, it's pretty well mixed. And to show you that, I can put a little bit more dye in. And it mixes very quickly. And so this idea of mixing, which you're all familiar with in your kitchen, is very closely related to these ideas of chaos that we've been talking about today. Things mix only if they undergo some kind of chaotic motion. Periodic motion doesn't produce mixing. Now, while we're talking about gases and liquids, I'll bet many of you have at home a garden hose. Do a lot of you have such a thing? That's right. Here's something you can do that will really annoy your parents. Don't tell them I said this, but go out sometime and turn on the garden hose full blast without holding on to the end of it. What happens? Have any of you ever done that? That's right. You're saying it with your arms. It goes round and round in a crazy fashion, right? There's actually a name for that. Bet you didn't know that. It's called the fire hose instability. Can you guess why it's called that? That's right, because firemen have to be very aware of this, because with their big hoses and the big fire hydrants, if you were to ever turn on a fire hydrant full blast with no one holding the end of the hose, it could flail around and actually injure someone very severely. So the fire hose instability is a very important example of chaos. And it just so happens that we have a fire hose. Well, not quite. It's really an air hose, like you would pump up the tire in your bicycle or your car. But it does exactly the same thing. It doesn't matter whether we use air or water. When the air comes out the end, it goes around in a very complicated manner. It's deterministic, it's predictable, but it is very erratic. And so the fire hose instability is an example of chaos. Now, while we're talking about the motion of gases, I want to show you a very interesting example of gases in motion. And to do that, I'm going to light a candle right here. And we're going to turn off some of the lights. And you're going to have to look at this through the television monitors, because it makes a very small image here. And it will show up on the monitor here once we get it focused. And you'll also be able to see on the monitors on the side. Now, while we're setting it up, I should point out that what we have here is a light source. The light goes through a prism which separates it into colors. Those come down and are reflected off a parabolic mirror. Remember that word? Parabolic mirror. Goes over the top of the flame, reflects off another mirror down there, into a mirror here, through a lens, and into the camera. Got all that? Now, you know light doesn't travel in exactly a straight line. If light travels through a region where there is a change in temperature of the air, the light will bend ever so slightly. And that shows up as colors. At least I hope. Let's turn it off and see. Now, it looks like smoke rising off the candle. In fact, it's rising upside down. Because of the lens, the whole thing is upside down. So the candle is actually at the top of the picture, and you can see the rising air currents above the candle. And in fact, if you look carefully, you notice that sometimes the air is moving in a smooth fashion. We call that laminar flow. And other times, when a little gust of air comes up, it moves in a more complicated, turbulent fashion. And that's an example of chaos. Now, I'm going to try something, and we'll see if this works. It's kind of tricky. I'm going to take the candle away. Let me warm my fingers up by rubbing them on my coat here. There you go. And that shows how sensitive this is to very small changes in the air temperature. The temperature of the air affects the light in such a way that it bends slightly, and that gives us colors. Now, this apparatus is called a Schlieren apparatus. Schlieren is a German word that means streaks. And indeed, that's what you were seeing. Colored streaks indicating the motion of the light moving through the air. Have you ever wondered what would happen if you would take a television camera and point it at the monitor that's connected to the camera? You ever wondered? Let's try that. See on the monitor here, we have a monitor, and inside of that we have a monitor, inside of that we have a monitor, and then more and more and more, and they go on forever. It repeats over and over and over again. Now, I want you to notice something else. You'll notice that if we adjust the camera in just the right way, that the image will change by itself in time. First it's bright, and then it's dark. Isn't that amazing that nothing's moving? We have the television camera pointing at the monitor, and yet it's changing. It's doing all kinds of interesting things. It's an example of chaotic behavior. Old Faithful. So, this is what we sometimes call video feedback. Have you all heard of audio feedback? Do you know what that sounds like when you get audio feedback? That's audio feedback, right? Now, audio feedback occurs for a reason that's very similar to video feedback. Because with audio feedback, that happens when the microphone gets too close to the speakers. Well, our speakers are up there, those blue things on either side. Our microphone, we have several. One's down here on the floor. That's the one I turned on. And by turning the volume way up, the sound from the speaker goes into the microphone. The microphone goes back to the speaker, back to the microphone, round and round and round and round. And it does a periodic sort of thing. It makes a sound that, in fact, is a periodic vibration of the air, much as our video feedback exhibited a periodic motion of the picture. I'll bet I can now show you a sound that you have all heard before. A dripping faucet. Now, you know, every house has at least one of these. There's a law somewhere that you can't own a house unless there's at least one faucet that does this, even when you don't want it to. But I want you to notice that the dripping is very regular. It's just like the metronome. But there's something interesting you can do with the dripping faucet, and you can all go home and do this. if you turn it up a little bit so it drips faster, suddenly it's not regular anymore. It's exhibiting chaotic behavior. Now, this is something you can all do at home, and I would encourage you to do the following thing. Instead of just adjusting it so that you get periodic behavior and chaotic behavior, look very carefully just at the transition where it stops being periodic and becomes chaotic. In fact, you know, this has been studied a lot. There's even a book called The Dripping Faucet. And it's not a children's book. It's a book for scientists, because there's a lot of good science in a phenomenon as simple as a dripping faucet. Well, you probably noticed while we were doing this that there was some things over here with funny pictures on them. And I want to call your attention to that again. You notice that as I talk, this one in particular is vibrating up and down in a very complicated sort of fashion, as if it were chaotic. But in fact, it's not. It's just responding to the air pressure variation that accompanies my speech. On the other hand, there are sounds that are extremely regular and extremely periodic, and I want to show you one right now. That's a sound that, in fact, we call a sine wave. A sine wave is the simplest kind of sound. It is just an up and down vibration, much like the pendulum vibrating back and forth. The air pressure is big and small in a very regular, predictable way. Now, sine waves can have high frequencies, or they can have low frequencies. But in each case, no matter whether the frequency is high or the frequency is low, it is nevertheless a periodic sound. Very regular, very repeatable. And you might be tempted to think that all sounds are like that, but of course they're not. And I want to show you now an example of a sound that is nothing like the sine wave. And I'll turn it on, and then I'm going to ask you where you've heard this sound before, so listen carefully. Where have you heard that? A television set, that's right. If you tune it between stations, or after the station goes off the air sometimes, you'll hear that sound. And you know there's a name for that. It's called white noise. You want to know why they call it white? You all know, I'll bet, that white light is made up of all the different colors, right? All the colors of the rainbow make up white light. Well, in exactly the same way, all of the different frequencies or pitches make up white noise. So you can make white noise by combining all of these different sine waves with all different frequencies together. Now, there are many kinds of noise. In fact, white noise is only one kind of noise. I now want to show you what we call pink noise. Listen to the difference. First white, now pink. Now, you can hear the difference. Pink noise somehow sounds lower, doesn't it? And that's exactly what it is. Pink noise has more of the low frequencies in it and not so many high frequencies. And we call it pink because pink light has more red and less blue. And red is like the low frequency part of sound. So we can make many different kinds of noise. Now on the computer, we have some of these different kinds of noise. Here's what white noise looks like on the computer. And that looks a lot like what it looked like on the oscilloscope over here when we turned it on. But I think it's a little easier to see on the computer, and there are many interesting things we can do once we have it on the computer. But first, let me show you what the pink noise looks like on the computer. It looks quite a bit different. It doesn't go up and down quite so rapidly. In fact, it has more low frequencies associated with it. Now, are there people in the audience that know how to read music? Quite a few people know how to read music. Well, that's good, because you can imagine that each of these little points is a note on a musical scale, and it goes up and down in a complicated fashion, a random fashion, in fact. And we could ask ourselves, what would that sound like if you were to play it on a musical instrument? Well, conveniently with the computer, we can do that. Have you all heard of Pink Floyd? Well, this is music by Pink Noise. Now, let me show you one other kind of noise. This is what we call brown noise. Brown, that's right. Brown noise has even more low frequencies in it. You see, it just kind of wanders around above and below the baseline there where it starts. Okay, now, while we have these electric circuits over here, I want to show you an example of chaos in electricity. I bet you didn't know that chaos, these kinds of things we've been talking about, can also occur in electric circuits. And we have an electric circuit that's extraordinarily simple. And I have it right here. This is a very simple electric circuit that has only two components. It has something that we call an inductor, which is just a coil of wire. And it has something that we call a diode, which is like a transistor in a transistor radio. And with just those two things, we can produce chaos. Because at the input of this circuit, we make a sine wave, a voltage, that's like the sine waves we were showing you over there. And at the output comes chaos. And it's truly amazing that circuits do this. And in fact, we can also explore the transition from periodic to chaotic behavior in this circuit. Now, we have the circuit over here, and we have it hooked up to the PA system, so you'll actually be able to hear it. So let me turn it on. Can you hear that very shrill pitch? Now, if this bothers you, just close your ears. I know some people are sensitive to this. But that is an example now of a periodic sound. It's a very high-pitched tone. It's about 12,000 cycles per second. And it's going into the circuit, and coming out of the circuit is, in fact, the same pitch. And that's what you're hearing. A single frequency, 12,000 cycles per second, quite regular and repeatable. But if I turn up the voltage at the input a little bit, now you're hearing a 6,000 cycle per second. It's exactly one octave lower. Now I'm going to turn it up a little bit more. You hear what happened? I'll turn the volume down so it doesn't, not quite so piercing. Another tone came in, exactly half of the previous one, 3,000 cycles per second, one octave below. And if I'm very, very careful, I can turn it up and get yet another. It's right there. It's a little hard to hear. It's not very loud, but a new tone comes in even lower. If I turn it up a little more yet, in fact, you will hear the sound of chaos. So you see, it's a sound a lot like the random sound that we have from the noise generator, but in this case, it is a deterministic sound. It's completely predictable, and it comes from a very simple electronic circuit. Now, in electronic circuits, there are several ways to make electronic circuits that are chaotic, and we have one here that consists of 6 neon bulbs. And the neon bulbs, you notice, are flashing, and they are flashing in what looks like a complicated, and in fact, it looks like a random sequence. It looks like you can't really predict which will go next, but in fact, it is quite a deterministic system. And what happens next is determined by what happens previously. But yet, it is very sensitive to initial conditions, and depending on just how we start it, the sequence of numbers is very complicated and very difficult to predict over the long term. Now, this one, too, we can simulate on the computer. And so on the computer, we actually have 8 neon bulbs, little bars, black bars, and you see every now and then one of them flashes red. And that's to simulate when that particular light bulb flashes. And you notice it's a complicated pattern. Do some of you play the piano? Quite a few. These kind of look like the white keys on a piano board, don't they? That's right. And so you might wonder what this music would sound like if you could actually listen to it. And in fact, we can do that with the marvel of a computer. So you see, it does sound a little bit like music, right? It's not great music, I agree. But it does have this combination of a certain degree of determinism that's characteristic of chaos. Music, you can't just mix in any old notes. There are rules for writing music. But on the other hand, it can't be too predictable either, or it would be boring. So music, in fact, combines a certain degree of predictability with a certain degree of unpredictability, and that's when it sounds best. And indeed, with chaos, we can produce music using deterministic schemes. Remember when I started the lecture, I mentioned a word, and I told you I was going to come back and ask you what it was? What was it? What? Fractal. That's right. The word was fractal. And a fractal is a complicated sort of object that is not a line, and it's not a surface, and it's not a solid. It's somewhere in between. And in fact, the spark that comes off the top of this Tesla coil is an example of a fractal. So we're going to turn it on again just to let you look at that shape and focus your attention on the shape of the spark that comes off the top of the Tesla coil. So that's a fractal. Now, you know, in nature, we often talk about things that are one-dimensional, like a string has essentially one dimension. It has length and not much else. There are other objects, like a sheet of paper, for example, that are two-dimensional because it has a width and it has a height, but it doesn't have much thickness. And so this is what we call a two-dimensional object. Then there are other things in nature that are fundamentally three-dimensional, like a ball, like this tennis ball, has three dimensions. But even these objects, the dimension depends upon your point of view. If you were a long way away looking at one of these objects like the ball, it would simply look like a dot, a point. It would have no dimensions. We say it has 0 dimensions. Now, nature is full of objects that don't have simple dimensions. What's this? That's right, a stick. If you were a long way away, the stick would just look like a dot. It would be a point with no dimensions. As you get a little closer, like those of you in the back row, it looks like a one-dimensional object, a line, right? As you come down closer, some of you toward the front, see that it has a certain thickness. It looks two-dimensional. If you come up even closer, as I am, you see, in fact, it's three-dimensional. And that is a characteristic of a fractal. It is an object that doesn't have a simple integer dimension. We can make examples of fractals. Have you seen a fractal that looks like that somewhere? That's right. It looks just like a snowflake. A snowflake is a fractal. It's clearly not a line. It's more complicated than a line, but it's not a surface either. It is less than a surface and more than a line. In fact, it is an object with a fractal dimension of 1.5, 1.5. It's halfway between a line and a surface. The other interesting thing about this fractal is if you look at any piece of it, like a little piece down in here somewhere, it replicates the entire object. It has a property that we call self-similarity. It's the same on all scales. Whether you look at it big or whether you look at it small with a microscope, you see exactly the same structure. And that is a characteristic of fractals. Now here's another example of a fractal. It goes by a neat name called a Sierpinski gasket. And in fact, it's a big triangle, but if you look carefully, you notice inside this big triangle are some smaller triangles. Inside of each one of those are smaller triangles yet. Inside of each of those are smaller. And as closely as you want to examine it, you see triangles inside of triangles inside of triangles. And it has the property of self-similarity. One can do the same thing with squares. If you start with a big square, like a sheet of paper, and if you cut a strip out from top to bottom, let's say a third as wide as the square, do the same thing horizontally, you make 4 squares. You can then take each of those squares and do the same thing, and if you do it over and over and over again, you make a fractal. It is something that's more than a line, but less than a surface. Well, here's a fractal I bet you've all seen. What does that look like to you? That's right, a leaf, and someone said a fern. In fact, that's what it is. It's an image of a fern, and it is a kind of a fractal, and nature is full of such fractals. And this one also has this property of self-similarity in that any little piece of it is just like the whole structure. Sort of rotated and twisted, but it has all the same characteristics. And in fact, it might surprise you to know that this pattern is generated by specifying only 8 numbers. And if I told you the 8 numbers, and if I told you the rules as to how you make the pattern, you could go and produce this pattern. And this probably has something to do with how biological species can reproduce with a very small amount of genetic information in the genetic code, because it's coded in such a way that it can be replicated on larger and larger scales until eventually we have people and things like that. Okay, so these are fractals. One last example of a fractal. Those were what we call deterministic fractals, produced by a certain rule, a mathematical equation that we just apply over and over. There are also things called random fractals. And one way to make that is to imagine you had a little grain of dust, and it was sticky. And you put it somewhere in the middle of a dust storm, and so every other dust particle, whenever it happened to hit it, it would stick. And then it would become sticky, and then other dust particles would collect. You would collect an object that has a very complicated looking shape. In fact, it is a fractal. It has a dimension of about 1.6 in this case. And this process, which is very common in nature, is something called diffusion limited aggregation. A long name, but that is one way that nature makes fractals of this sort. I'll leave that on for a while I'll show you an example over here that involves magnetism. Now over here we have two coils of wire, these red coils, that carry electric currents, a strong electric current, and they make a magnetic field in the region in here. And I can take an aluminum ball that's hollow on the inside, and I can put it in the magnetic field, and it levitates. There is a magnetic force. Now, you might note that aluminum is not normally a magnetic material, but in this case, it becomes magnetized because it's an alternating electric current, and that induces electric currents in the ball, which are then attracted and repelled by the currents in the magnets. We have down here some more of this liquid nitrogen, and in the liquid nitrogen is another cylinder of aluminum. I'm going to take it out, and it's also hollow, and so you can see some liquid nitrogen was inside, and it's now coming out through the hole there. But the point is that this cylinder is now very, very cold. It's at 321 degrees below 0 Fahrenheit, and I'm going to put this in the magnet and turn it on, and you will notice it moves in a complicated, in fact, chaotic fashion, and after a while it starts to spin around quite violently, and I'll turn it off before it comes out and injures somebody. Because I want to point out that that is a complicated, chaotic motion that, in fact, no one understands. There's a debate right now in the scientific literature going on as to why, in particular, that thing spins around like that. And no one quite understands it yet. So there are many things that science can't explain. If a scientist ever tells you that he or she understands everything, don't believe him or her, because there are more things we don't understand than there are that we do. Well, I want to show you one last example here that in fact involves randomness. Now, one can say that really all things in nature are deterministic. We believe we know the fundamental physical laws, at least for classical physics, that govern the behavior of everything. So when we see something complicated in nature, we are tempted to say, in fact, it's chaos. But there are things that we believe are truly random. And I want to show you an example of something that, so far as we know, is completely random. And I have it over here. I'll turn it on. Can you hear something clicking? Do you know what this is called? That's right. It's called a Geiger counter. And it works because there's something here called a Geiger tube, which is sensitive to nuclear radiation. Now, I'll bet a lot of you didn't know that there's radiation bombarding us all the time from outer space. Did you know that? It's called cosmic rays. And if you listen, every now and then it will click. And whenever it clicks, that's when a cosmic ray happens to go through this little tube here. Now, every second or so, a cosmic ray is going through every one of your bodies. And you don't feel it, doesn't bother you, and it's harmless, so far as we know. But it is important that there are many kinds of radiation in nature. Now, since cosmic rays don't come very often, we have a radioactive source here that is much more powerful. Now, a lot of people, you know, are scared of radiation. And just like with electricity or fire or any other thing, there's reasons to be scared of certain things, especially if you don't understand them. But on the other hand, if one does understand, and if you treat these things with respect, they are not intrinsically harmful. It's only out of our ignorance and our superstition sometimes that we distrust things like radiation. But anyway, this is a kind of a radioactive source, And the thing I want to point out is that the clicks of the Geiger counter occur, so far as we know, in a completely random pattern. We think that the underlying physical laws that govern the radioactive decay that's making the clicks is a law of probability and not a law of determinism. And this is the very thing that disturbed Albert Einstein to his dying day. He never quite believed that there were processes in nature that were inherently random and not deterministic. Well, the one last thing I want to do is to show you an example of chaos or randomness that involves light. Before I do that, I want to bring out our liquid nitrogen cloud. And I want to remind you of something I said early on in the lecture. Remember the butterfly effect? Now, sometimes some of us feel like we're not very important in the world, and we feel like maybe our lives don't really count for a lot, and there's not a lot we can do to change the way the world is. But remember the butterfly flapping its wings in Brazil, setting off tornadoes in Texas? Well, every one of you have that same possibility, that any small act on the part of any one of you can be amplified over the years and years and can have dramatic, important effects on the course of human history. So don't ever let anyone tell you your life doesn't count. So with that, I want to turn on our strobe light here, which in fact is connected to the Geiger counter. I'll put on my hat, and I'll thank you all for coming.